we're going to talk about a brand new kind of function. Actually, there's several of them. I bet you've never seen them before. They're called the hyperbolic functions. And there are going to be 6 of them. The first one is called hyperbolic sine. So notice it looks just like SIN, but we put an H on there for hyperbolic. Hyperbolic sine is defined as e to the x minus e to the negative x over 2. And then, as you would guess, if there's a hyperbolic sine, there's a hyperbolic cosine. So we have hyperbolic cosine of x is e to the x plus e to the negative x over 2. Well, then, obviously, if there's a hyperbolic sine and a hyperbolic cosine, there's a hyperbolic tangent. How would you define hyperbolic tangent? Hyperbolic sine over hyperbolic cosine. So now you begin to see why the name sine, cosine, and tangent are coming in for hyperbolics. Hyperbolic cosine is hyperbolic sine, or hyperbolic tangent, is hyperbolic cosine divided by, one more time, hyperbolic tangent is hyperbolic sine divided by hyperbolic cosine. So there's half of the new functions. What are the other half? The cofunctions, they're called. So we've got hyperbolic cosecant is 1 over hyperbolic sine. And for this one, we have to have a little rule, x can't be 0. How come x can't be 0? You would be dividing by 0, because notice if I plug 0 into hyperbolic sine, I get e to the 0, which is 1, minus e to the 0, which is 1. 1 minus 1 is 0. So if x is 0, you get 0, you get 0 on bottom. That's a bad thing. And then, of course, there's hyperbolic secant. That's 1 over hyperbolic cosine. And finally, hyperbolic cotangent. That's 1 over hyperbolic tangent. And same deal for that one. We got to have x cannot be 0, because if x is 0, you would have 0 down on the bottom.
So the force secant stays in the same rule?
No, you don't need it for that one, because notice if I plug 0 into the hyperbolic cosine function, I have e to the 0, which is 1, plus e to the 0, which is 1. 1 plus 1 is 2. I won't have 0 on bottom. So I don't need to say x can't be 0 for that one.
Is there any number which it can't be for that?
No. The domain, well, that's a good question. What's the domain for hyperbolic sine? What kind of numbers can you plug into that? Can you plug in 0? Yeah. Can you plug in positive numbers? Can you plug in negative numbers? Yeah, you can do e to the negative 3, can't you? Yeah, so what's the domain for hyperbolic sine? Other numbers. How about the domain for hyperbolic cosine? All real numbers also. Again, I can plug in 0, I can plug in positives, I can plug in negatives. Domain for hyperbolic tangent? All reals, because I'm not going to have to worry about a division by 0. I don't think that function can never be 0. How come that function can never be 0? What can you tell me about e to a number? It's always positive, isn't it? So I've got e to a number, this is going to be positive, plus e to a number, that's going to be positive. So this hyperbolic cosine is always what kind of number? It's always a positive number. So I'm never going to have 0 on bottom there, so that one's all real numbers. And so these are all real numbers except 0, except for the hyperbolic secant. That one is also all real numbers. Questions on that?
Will our calculators do anything with these?
Will our calculators do anything with these? You mean like graph them?
Yeah.
Sure.
Well, also, is there like a function already built into it?
You mean like a hyperbolic sine button?
Yes.
Yes. The question is, where did I find that?
Well, I'm not certain on that calculator, but I have this button I just push and it brings up every
Okay, but these are not trigonometric. These
Well,
are
yeah.
hyperbolic.
It brings them up.
All right. So, anybody find the hyperbolic sign button yet?
Your catalog.
Under catalog, and I think that's the only place it exists.
Oh.
All right. So, if you want to find the hyperbolic sign or the hyperbolic cosine, you have to go into the catalog, which is second 0. And then, if you're clever, you push the button for S. The button for S is the LN button. Notice it has a little green S on it. That'll get you down to the S's at least. And then you can scroll down. So there's sine inverse, there's hyperbolic sine, and there's hyperbolic sine inverse. Yeah, once you have a function, you get an inverse function, don't you? That'll be after break. Thanks. So there's what the graph of the hyperbolic sine function looks like. It does look similar to tangent, except tangent would repeat over and over again, correct? It also looks a lot like y equals x cubed. Y equals x cubed has that basic shape. But there is a difference. The difference is there are actually what we would call oblique asymptotes here. This graph, if I were to graph the function, I shouldn't have erased that. I'm going to regret that because I'm going to go back and find it again. If I were to graph the function e to the x, over 2, should be e to the x over 2. Yeah. You can't see it. So you would notice that the graph of e to the x over 2 is very, very close to the right-hand side of this graph. And the graph of e to the negative x over 2 would be asymptotic to the left-hand side. So it's not quite y equals x cubed. Y equals x cubed doesn't have those asymptote sort of things. So that's a strange asymptote. You don't normally see exponential asymptotes. So looking at that function, though, what's the range of that function? All real numbers, negative infinity to infinity. That's correct. All right, now let's graph the hyperbolic cosine function. Again, the only place I know of to get it is in the catalog. And then I push the C button. And I scroll down, down, down. There it is. It looks like so. What's the domain of that? The domain is all real numbers. What's the range of that function? Greater than or equal to 1. What's that function look like? Looks a lot like a polynomial. Looks a lot like a parabola. But again, it's not a parabola. It has asymptotes of e to the x over 2 in that direction. Anybody ever seen a graph that looks like that before?
Squared.
It looks like x squared plus 1. I agree. That's not what I meant. I meant when you're outside walking around. Anybody ever seen a shape that looks like that before?
You're upside down.
If it were upside down and you were in St. Louis,
See it.
you would see that shape. The St. Louis arch is in the shape of a hyperbolic cosine function. And there's a name for that kind of graph. It's called a catenary. Catenaries are very special functions. And the reason the St. Louis arch, and many arches, in fact, are in the shape of a catenary is they are very self-supporting. If you build this shape and stand it up, it needs almost no support at all to remain standing. Years and years ago, there used to be a science center over in the Arnott Mall. And they used to have these little blocks, and they were numbered, and you would put the blocks together, and the bottom ones looked like this, and then they had slight cuts on them, and you would put the next one here, and it had a slight cut, and it would form an arch. Oops, I drew to the wrong side. And this arch, you would build it on a table, and then the table was hinged, and you would lift the table up, and put it back down, and the arch would stand there by itself with no glue, no nails or anything. But it's very self-supporting. The blocks will itself hold it together, which is kind of cool. So the St. Louis Arch, during its construction, actually had very little side support holding it up as they were building it. It's self-supporting. All right, how about if it goes this way? Anybody ever seen a catenary in that direction?
On suspension bridges.
Suspension bridges. If you take a flexible cable and you hold it on two ends, it will form an arch. And most people think that arch is in the shape of a parabola. It's not. It's in the shape of a catenary. So in a suspension bridge, the big cables connecting the towers, those are in the shape of catenaries.
So what's the difference between a parabola and a catenary? Like the shape?
Well, it's very subtle. It's hard to tell by looking at it.
Oh, it's flatter at the bottom.
It's flatter at the bottom. So yeah, if you compare that to the graph of y equals x squared plus 1, they're pretty close. But I think as you zoom out, you can see they start to separate as you zoom out. Okay? So most arches used in building construction are actually in the shape of catenaries. The telephone lines outside, look at the telephone lines, they sag a little bit. That's the shape of a catenary. Questions on that?
So if you have the upside down one again, could that kind of be the shape of like a flat bridge with like just the catenary hollowed out?
Possibly, yes. So I think what you're saying is bridges are quite often built like this.
Yeah.
Yes, it's very likely that this curve is in the shape of a catenary. Very likely. And actually, bridges are never built flat. Well, not if they're built well. Why not?
Flex from the weight.
They flex from the weight. So when you build a bridge, you actually crown it a little bit, so that as it starts to sag, it straightens out, not actually sag and have a big dip. So if you've ever done building construction, even if you're building a deck for a house, or if you're putting a roof on, when you go to put the boards on, before you put them on, you always look at them and you see which way they're warped, and you always put them so the crown is up, so that when you put weight on them, they sag and straighten out. And so most roadways and most bridges are built that same way too. They're not actually flat.
Also, it prevents water from pooling on.
And it prevents water. Right? Roads are built so they're high in the middle and low on the sides, and so the water flows off. That's correct. Other questions? All right. So other than the way these are defined, I mean, we could call this anything and call that anything, and then we could divide them and call that a new function. Why sine? Why cosine? Oh, sorry.
Isn't the for hyperbolic functions or the corresponding function which does arc length, which is the length of the segment of the circle or something?
Correct. That's where the connotation with hyperbolic comes in, actually. The hyperbolic comes in with, has to do with areas and arc lengths. But why sine and cosine?
Based off of the triangle thingies.
Not so much. These functions have a lot of properties that are very, very similar to the sine and cosine function. For example, one of the most famous things you might remember about sine and cosine. Sine squared x plus cosine squared x equals 1. And that has a famous name. That's the Pythagorean identity. The same doesn't quite hold true for hyperbolic sine and hyperbolic cosine, but it's close. Hyperbolic cosine squared minus hyperbolic sine squared equals 1. And just for the heck of it, let's prove that one. So I'm going to take my hyperbolic cosine. Hyperbolic cosine was e to the x plus e to the negative x over 2. And then I'm going to square it. minus hyperbolic sine was e to the x minus e to the negative x over 2. And then I'm going to square it. And I'm going to see if I can do some algebra and simplify that and make it equal to number 1. Well, what would you do? How would you simplify that? Well, what do you get when you square e to the x plus e to the negative x?
2x plus e to the negative 2x.
Close. You're missing something. What do you have to do when you take x plus 4 and you square it? You got to do x plus 4 times x plus 4, and you got to FOIL it out, and you get some middle terms. Same thing happens here, you get middle terms. So you square this, you square the first one, what's e to the x squared? E to the 2x. And then you multiply the two things in the middle, and you multiply them by 2. What's e to the x times e to the negative x? No? No? E to the 0. You add your exponents. When you multiply things that have the same base, you add your exponents. E to the 0 is a fancy way of saying 1, but then I got to multiply that by 2 because I get 2 of them, so that's plus 2. Plus e to the negative 2x. And that's going to be over 4 because I square the bottom. Minus. And then I do the same thing again. I can square the bottom, that's 4, that's easy enough. I square the top. E to the x squared is e to the 2x. I multiply these two things together. Again, my exponents add up to 0, so I get a negative 1. But then I have to multiply it by 2, so I get negative 2. Plus e to the negative 2x. Now, look what happens. The denominators are the same, so we can go ahead and we can add the numerators. What's e to the 2x minus e to the 2x? 0. Those cancel out. What's 2 minus negative 2? 4. And what's e to the negative 2x minus e to the negative 2x? 0. You end up with?
You wrote that out because that plus e to the negative 2x is a fraction.
Here, this plus?
No, I see.
That should be a plus, but then I've got this minus out front here. Which,
Because you
cause,
squared it.
right, because I squared this thing.
Yeah.
A negative times a negative is a positive. So I do indeed get the number 1. Questions on that? All right. What other famous trig identities do you know? All right, so you can do the same thing if you have sine squared x plus cosine squared x equals 1. Again, that's the Pythagorean identity. What happens if you take everything here and you divide it by cosine squared? What's sine squared over cosine squared? Tangent squared. Plus cosine squared over cosine squared is 1 equals secant squared x. I can do the exact same thing with the hyperbolics. I have hyperbolic cosine squared minus hyperbolic sine squared equals 1. I could do the exact same trick and divide everything by hyperbolic cosine squared. What's hyperbolic cosine squared divided by hyperbolic cosine squared? That's a mouthful. Minus what's hyperbolic sine squared divided by hyperbolic cosine squared? Hyperbolic tangent squared. And equals hyperbolic secant squared. So again, you get not exactly the same formula, but a formula very, very similar. Questions on that? And we could do the same thing. I'm not going to do it. We could do the exact same thing and divide everything by sine squared, and come over here and divide everything by hyperbolic sine squared, and we get another very, very similar formula. Any other famous trig formulas you know? How about this one? Anybody remember that formula? Sine of u plus v? No? That one is sine u cosine v plus sine v cosine u. The formula for hyperbolic sine is exactly the same. Hyperbolic sine of u plus v is hyperbolic sine u, hyperbolic cosine v, plus hyperbolic sine v, hyperbolic cosine u. Keep switching my hyperbolic sines and my hyperbolic cosines there. How about the formula if I had a minus in the middle? How does that change for trig? Anybody remember? If I have a minus there, I get a minus right there. Same thing works with hyperbolic signs. If you have a minus right there, you get a minus right there. How about the same formula for cosine? Anybody remember the formula for cosine u plus v? All these important formulas you guys don't remember. This one's cosine u cosine v minus sine u sine v. For hyperbolics, it's not exactly the same, but it's close. Hyperbolic cosine of u plus v is hyperbolic cosine u, hyperbolic cosine v, plus hyperbolic sine u, hyperbolic sine v. Almost the same. Again, formulas aren't always exactly the same, but the formulas are always close. Questions on that? All right, and then the most important formulas. I was hoping people would say that they knew about trigonometry. These formulas I do know you know, but you better know them. What's the derivative of sine? Cosine. What's the derivative of cosine? Negative sine. Oops. I meant to put a hyperbolic in there. What's the derivative of hyperbolic sine? Well, a good guess would be
Hyperbolic cosine.
hyperbolic cosine would be a very good guess. But is it wrong? Well, let's figure it out. If I wanted to take the derivative of hyperbolic sine, I would take the derivative of e to the x minus e to the negative x over 2. So that's going to be something over 2. What's the derivative of e to the x? E to the x. Minus. What's the derivative of e to the negative x?
Negative e to the negative x.
Negative e to the negative x. You've got to use a chain rule there, but I've already got a negative, so that's going to make it a positive. That is hyperbolic cosine. So the derivative of hyperbolic sine is hyperbolic cosine. Same rule, that's nice. How about the derivative of hyperbolic cosine? A good guess would be negative hyperbolic sine would be an excellent guess. Let's see if it's correct. That would be the derivative of e to the x plus e to the negative x over 2. What's the derivative of e to the x? E to the x. Plus, what's the derivative of e to the negative x?
Negative e to the negative x.
Negative e to the negative x all over 2. While your guess was an excellent guess, it was not correct. The derivative of hyperbolic cosine is hyperbolic sine. No minus sign there. So it's even better in that sense. You always had to keep track of your signs when you were dealing with trig functions. Not so much anymore. What's the derivative of hyperbolic tangent? Hyperbolic secant squared? That one's correct. How about the derivative of hyperbolic cotangent? What's the derivative of cotangent? Negative cosecant squared. So what's the derivative of hyperbolic cotangent?
Cosecant squared.
Actually, there is a minus sign there still. Good guess. It's negative. If you don't believe me, simply write it out. Write out cotangent as cosine over sine, hyperbolics. Use the quotient rule and see how it works out. And then, of course, there's two more. The derivative of hyperbolic secant. What's the derivative of regular old secant? Secant x tangent x. This one has a minus in it. Minus hyperbolic secant, hyperbolic tangent x. And then finally, the derivative of hyperbolic cosecant. I don't believe this one has a minus sign. Oh, it does. This one has a minus sign too. Minus hyperbolic cosecant, hyperbolic cotangent. All right, so here's the kind of homework problems we're going to see. F of x is hyperbolic cosine of 8x plus 1. Bless you. Bless you. We want to know the derivative. What's the derivative of hyperbolic cosine of 8x plus 1? Hyperbolic sine of 8x plus 1 times 8. Where did that times 8 come from?
Derivative of the inside.
Derivative of the inside, absolutely. You have to use the chain rule.
Shot. Or I got it right.
Yeah, it was a good shot. Chain rule is still there. Doesn't change. How about, I tried to trick you. It didn't work. G of x is the natural log of the hyperbolic tangent of x over 2.
I'm going to say hyperbolic cosine of x over 2 over hyperbolic sine of x over 2.
1 over hyperbolic
One over
tangent x
the-
over 2 times.
All right, so I got to use my logarithm rule. My logarithm rule says 1 over whatever's inside there. So it's 1 over hyperbolic tangent of x over 2, which is hyperbolic cosine over hyperbolic sine, which is what you were saying.
That's right.
I know. Times, but we're not done yet.
Oh.
Secant squared.
Because then we have to use the chain rule still, don't we? We've got to take the derivative of hyperbolic tangent. What was our derivative of hyperbolic tangent?
Hyperbolic secant squared.
Hyperbolic secant squared of x over 2
Times the derivative of x over
times the derivative of the inside again. So this is a double chain rule problem. And the derivative of x over 2 is half. Questions on that one?
You got me there.
Forgot your chain rule that time, didn't you? Yes, you did. All right, how about another derivative problem here? There's got to be a good one. g of x, using g again, g of x is x squared hyperbolic secant squared of 3x. What am I going to do this time? Product rule. G prime of x is, I'll do the hard part, the derivative of the first is 2x. I leave the second one alone. Plus, now I leave the first one alone, that's x squared. Now comes the fun. What is the derivative of hyperbolic secant squared of 3x?
Negative hyperbolic secant of 3x.
That's 3.
No, hyperbolic tan of 3x.
Did you bring the 2 down?
Oh, wait.
Ah, we have to use, this is another double chain rule.
Okay.
We got to deal with this 2 first. That's the thing furthest outside. So the 2 comes down, and we leave everything else alone. So we're going to have 2 hyperbolic secant of 3x. But then I need to multiply by the derivative of the inside. In this case, I need the derivative of hyperbolic secant. What was our derivative of hyperbolic secant?
Negative hyperbolic secant x, and then hyperbolic tan x.
That sounds right. That one had a minus in it. So I'm going to have minus hyperbolic secant of 3x times hyperbolic tangent of 3x
Times 3.
still not done, times 3. Again, it's a double chain rule problem. I've got to take the derivative of the inside again. Questions on that? All right, well, if derivatives are that much fun, imagine how wonderful integrals are going to be. You don't think that's how it works? How about the integral of hyperbolic cosine of 5x dx? Well, what if the 5x wasn't there? What's the integral of hyperbolic cosine x? Hyperbolic sine. And you don't have to worry about the minuses anymore. When you're dealing with just sine and cosine with hyperbolics, there's no minus signs to remember. So what are we going to do with that 5x? This is a u substitution problem. U is 5x, which makes du 5 dx. So we need a 5 dx, which means we need a 1/5. This becomes 1/5 the integral of hyperbolic sine of u du. And the integral of hyperbolic cosine is hyperbolic sine. So this is going to be 1/5 hyperbolic sine of 5x plus c. So dealing with hyperbolic cosine and hyperbolic sine is actually a little bit easier than sine and cosine because there's no minus to worry about. They always turn out to be positive. So that's a little bonus. Not much of a bonus, but a little bonus. How about the integral? Of hyperbolic cosine x times hyperbolic sine x dx. U equals hyperbolic cosine? What told you in this problem you need to use U substitution? We don't have a product rule. We can't integrate multiplication. That's exactly right. So that should tell you, as soon as you see that multiplication there, that this is a U sub problem. So you chose to let U be hyperbolic cosine, which is just great, because derivative of hyperbolic cosine is hyperbolic sine. So this becomes the integral of U du. That's a half U squared plus c. So we have 1/2 hyperbolic cosine squared x plus c.
Does it matter if we chose sine?
Would it matter if you chose sine? I don't think so. Again, one of the nice things about dealing with hyperbolics is your minus signs. If we let u be hyperbolic sine, du would still be hyperbolic cosine. There's no little minuses to have to worry about. So this would still be the integral of u du, which would still be 1/2 u squared plus c. The only difference is we would get 1/2 hyperbolic sine squared.
You have different C's, right? I think you figured it out.
That's an excellent question. Are these two functions exactly the same? No, probably not. I don't know. I'd have to check. But my guess is probably not. They probably differ by a c. They're probably parallel. So you might have to have c be 1 for this one and c be 0 for that one to make them work out to be exactly the same. But they might be exactly the same. I don't know. Questions on that? All right, one more integration problem. How about, oh, that's a good one. The integral of hyperbolic cosine divided by the square root of 9 minus hyperbolic sine squared x dx. That's what we were doing 2 days ago. If we start with a simple u substitution, u is
Hyperbolic sine.
hyperbolic sine. Why do you want u to be hyperbolic sine? Because it will get rid of that hyperbolic cosine, won't it? So this turns into the integral of 1 over the square root of 9 minus u squared du. And you're right, that fits exactly into one of those patterns that we had back in section 5.7.
Sine.
This is the arc sine form. So this is the arc sine of u over 3 plus c. So final answer. One of the nicest functions you've ever seen, arc sine of the hyperbolic sine over 3 plus c.
And you can't cancel out the arc sine and the
Arc sine and hyperbolic sine are not inverses. That's correct.
Yeah, no, I thought that was.
Those do not reduce in any way, shape, or form, unfortunately. That is the best you can do right there. Go ahead and graph that. Yeah, you could see what it looks like. I have no idea what it'll look like. It will look like some sort of arc sine shape.